A hydraulic ram is a device that uses the hydrodynamics of water to lift a percentage of the water to a higher height. It's not that hard to understand conceptually where the energy could come from. It's much like a dam that dams up a reservoir of water. Some of the water flows down, runs through a hydroelectric generator, which turns a turbine, generates electricity that could be used to pump some of the water up to a higher altitude.
It's not that hard to put some simple energy limits on this process. Consider that we have a reservoir of water here. We're going to let it flow down a pipe into our hydraulic ram here, and then some of it is going to be released here as wastewater, and some of it is going to be pumped up to a higher altitude for our output. Now, we have a potential energy of the input water. We can calculate that based on the height here, call it HI, the height input of the reservoir of water above the ram. The input potential energy is going to be the mass of the water input flowing into the ram times the height times the acceleration due to gravity. Mass times force. Height times gravity being the force of gravity here. And likewise, there's going to be a height at the output, and that's going to give us a potential energy at the output of the mass output times the height of the output, again times acceleration due to gravity. And due to conservation of energy, we know that our output energy has to be no more than our input energy. So UO has to be less than or equal to UI. And we can just expand that out like this. Obviously the acceleration of gravity is the same in both cases, so it just cancels from both sides of the equation. We have this here, and now I can just divide through by MI on this side, and then also divide through by HO, and be left with this equation, which gives me a relationship between the ratio of the mass output to the mass input. So the mass output is the water flowing up here, the mass input is the water flowing down here, so we have a ratio between the amount of water, the mass of the water output to the mass of the water input in terms of the respective heights. So let's say our initial height is 1 meter, which is to say our reservoir is 1 meter above the ram, and let's say we're trying to pump up to a height of 10 meters. That would give us an HI over HO of 1 meter over 10 meters, which is just going to be 1/10 or 10%. And we multiply through by MI, we have this relationship here. So the output mass of water can be no more than 10% of the input mass. Likewise, if we're trying to go from a 1 meter height here to a 100 meter height of our output, that would be 1 meter over 100 meters, or 1/100th, or 1%. We could lift no more than 1% of the water. Of this water flowing down through a height of 1 meter, no more than 1% of it could be lifted up then to a height of 100 meters. The other 99% going out here as discharge from the ram. And this is really a hard energy limit, not just in the hydraulic ram, but on any energy-based or any water-based system. There's no way you could, for example, build a hydroelectric generator here to operate over these same distances and do better in terms of pumping some percentage of the water up to a higher height. you cannot get more energy out of the system than you get in. So that is a measure of, just based on the ratio of these heights, what percentage of water we can expect to get out if the system were to operate at 100% efficiency.
Energy. That tells us how much the device could lift, but let's look at how it works to actually lift the water. The key to the hydraulic ram is the impulse valve, which in our construction is built using a T. There is water coming in here on a hose, and then water going out here to what we'll call the delivery valve, but it's this impulse valve this part of the system, the spring-driven valve at the top of this lower T, that is the important. And let's kind of do a close-up on this part here. We have a closure, we have a plunger, we have a spring coming down here, and this is mounted to some fixed point. So as the water flows up into here, it pushes this closed, and then once it's closed, the water stops flowing, so the spring pushes it back open again. The water is able to flow again, it pushes it closed, and it's open and close, open and close, open and close. But we don't need to have the spring. In fact, the spring kind of confuses the issue a little bit, because the spring only serves to make the system oscillate, so it keeps running continuously. What we really want to look at is what happens to the valve when it closes. It's an open to close. It's an open to close transition. We have here tank of water, valve here. Water moving through the system, and then at some point the valve closes, and then sometime later the system has settled down into a steady state. No spring in this picture, just the water moving, valve closes, and then sometime later the whole system has become quiet. There's an energy difference between these pictures. The quantity of water is the same between the instant right after the valve closes here and the instant sometime later when the whole system has become quiet. Here we have the same quantity of water because the valve's closed, the whole system's closed. We have the same potential energy because the tube is completely filled with water, as is the reservoir in both cases. And yet here we have kinetic energy because the water is moving. And here there's no kinetic energy. So we've lost some energy in the picture, and we know from conservation of energy that the energy has to have gone somewhere. And the obvious question then is where? First of all, eventually it's going to go to friction. And basically that ultimately means a small increase in temperature. So the temperature of this system is a little bit higher than the temperature of this one, but really we want to look more closely at how did we get from here to here. What happens in the fractions of a second just after this valve closes? Well, what happens is that a wave, a shock wave, is generated which moves up the course of the flowing water. Behind the shock wave, in this region, the water is basically quiet at this point, while up here it's still moving. And this is a rough principle of information flowing at only a finite speed in any physical system. The ultimate limit would be the speed of light, but in a hydrodynamic system, the limit is the speed of sound. The speed of sound in water, that's the speed at which this wave is going to move up this pipe. And in the wake of this wave, there are going to be some important changes that are going to occur, and that's going to explain where the energy goes in this system. But let's look first of all at just some rough pictures of, or just some rough numbers, I would say, of what we can expect.
Okay, so let's look at what happens when the valve closes. Let's start with the assumption we just have a long pipe and an opening at the end through which water is flowing. There's the flow of the water. And then at some point, a valve closes here at the end of this pipe. We'll call this time 0, the time at which the valve closes. And then a short while later, we're talking maybe 1,000th of a second, maybe less, we have the closed valve here. We have a shock wave that has made its way some distance up the pipe. We'll call that D1. I'm calling it D1 because this whole region in here, I'm going to call this region number 1. The whole area from the end of where the valve is to where the shock wave has reached. Now, in the area upstream, the water is still moving. The water downstream in here, the water is basically static. Now, the wave moves at a finite speed. It's the speed of sound in water. We'll call it Vs, speed of the wave. And the distance d1 is going to be equal to the velocity of the wave, Vs, times the time t, and this is, we'll just call this t equals t, the time it took for the wave to move through this distance d1. So t times Vs is d1. Now at the same time this was happening, the time it took for the wave to move, the water up here was also moving. And if you look at any particular point of water here, it has moved a much shorter distance, but it has moved that distance because the water is also moving with the speed I'll call Vf, the speed of the flow. And what I'm most interested here in is an area right here that I'm going to call area number 2. And that is basically this, we'll call this, the width of it is going to be d2, and d2 is the velocity of the flow, Vf, times t. So, in the time t that it's taken the wave to move d1, d2 is the distance that the water has moved in that time, and in particular, from this point is the water that is now coincident with the wave. And the point is that since the water's been moving this way and the wave's moving this way, and they've both now reached this point here, all the water that was in both region 1 and region 2 now has to be compressed into region 1. So basically this water has moved like this in the time t. And what we now want to compute is what's that compression. So let's just assume that we have a pipe of constant area that we'll call A, area of pipe, the cross section. If we were to look at the end of the pipe, it would probably be something like this. That's the area A. And we want to compute the amount of water that's in region 1 and region 2, and then compute the area of region 1 and the density of the water, of the new water, that's been compressed into region 1. So let's start by computing the area, or I should say the volume of region 1 is simply going to be the cross-sectional area of the pipe times the length of region 1, which is D1 times A. And the volume of area 2 is also going to be basically the same thing. V2 is going to be the length of area 2, again, times the cross-section of the pipe A. The total volume is going to be D1A plus D2A, because that's the sum of the volumes. Now, the water has some initial density, which we'll call rho O, density being measured in units of mass over units of volume, or kilograms per cubic meter. The amount of water in this entire region V1 and V2 is going to be M, total mass of the water, is going to be the initial density times the total volume, D1A plus D2A. And this mass of water is going to be compressed into region 1. So we end up with a final density rho equal to the mass over the new volume, which is rho 0 times this expression over the volume, which is D1A. And we can immediately see that we can pull out rho O, and we can also factor out A, like so. We can cancel A, and then we are left with this. Except that we're not left with this, because we can come back to our expressions here for D1 as VST and D2 VFT and plug these in down here. So D1 is VST plus D2, which is VFT over D1, which is again VST. We see that again the times cancel, much as the areas did, and we are left with a final expression for rho. The new density of the water, the compressed water, is the initial density times Vs plus Vf over Vs. We could also factor out the Vs term and write this as rho 0 of 1 plus Vf over Vs. Now, just to get a rough idea of what kind of numbers we're talking about here, Vs, the speed of sound in water, is 1,460 meters per second. So, to obtain a 1,000th change in density, to increase this thing by 1%, Vf would have to then be what? 14.6 meters per second. No, I'm sorry, that would be a 1%. Let's just go with a let's go with 1.46. This would correspond to a 1/100th increase in density, 1% increase in density. This would correspond to a 1/1000th increase, a 0.1% increase in density. And just to get an idea of what speeds we're talking about here, a meter per second is going to be, let's see, there's 60 minutes in a second and 3,600 seconds in an hour, so this is 3,600 meters per hour, or 3.6 kilometers per hour. So 1.46 meters per second, let's just round it off and say 1.5 meters per second. That's going to be 3.6, half of 3.6 is going to be 1.8, 1.8, 5.4 54. So this is going to be right about 5.4 kilometers per hour, and this is about 54 kilometers per hour. So this is the speed here of a relatively slow car, 54 kilometers per hour, and this is a really not even a walking pace, 5.4 kilometers per hour. So we see certainly with this one, with a very reasonable flow rate of water, we can expect to achieve a 1/1000th increase in the density. And as we'll see in a minute, the increase in density of 1,000th is going to result in a much more significant increase.
The isothermal compressibility is a fluid property. It's approximately linear, and actually for most liquids it's a very good approximation for it to be linear. It's defined as negative of 1 over the volume times the partial derivative of volume with respect to pressure, constant temperature. Isothermal, constant temperature, and for hydraulic ram operations, temperature is, it is for all practical intents and purposes an isothermal process. There probably are slight changes in temperature, but they're insignificant. So, and we'll just assume linearity throughout the region we're working with, which is probably a pretty good assumption. Throw away the differential calculus and replace our differentials with deltas. So this just becomes 1 over V times delta V, the change in volume, over the change in the pressure, delta P. Now, we do need to get this from volume to density, because we were working with density, and this is in terms of volume, but the relationship between them is simple. Rho, the density, is defined as the mass over the volume. And we can bring volume out and just see that mass is equal to volume times rho, density. I just multiplied through by V. Well, if the mass is constant, and this is a constant, we're not adding or taking fluid out of the system here. We're just looking at pressure changes as the wave moves along the pipe. So the mass is constant, and that means any change in the volume must be offset by a corresponding change in the density. If the volume goes up 10%, the density has to go down 10%. So, simple relationship there, delta V over V, the percentage change in volume, is equal to negative delta rho over rho, the percentage change in pressure. So here we can just come over and we can write this as negative delta V over V times 1 over delta P, the pressure. We can use this relationship here to replace negative delta V over V with delta rho over rho times still 1 over delta P, the pressure. And if we multiply through by delta P and divide through by kappa, we get delta P is going to be equal to 1 over kappa times delta rho over rho. In other words, the change in pressure is going to be the inverse of the isothermal compressibility of the fluid times the percentage change in pressure and density. So now we go to, I'd rather do an experiment, or we go to a table. I went to a table in the CRC Handbook of Chemistry and Physics, looked up the isothermal compressibility of water at room temperature, and it gives us, what, 4.5 times 10 to the negative 4th inverse megapascals. So this is for water. And we need the inverse of this. So we're going to invert 1 over K, 1 over 4.5 is going to give us roughly 2.222 times 10 to the 4th, inverse of 10 to the negative 4th, and the inverse of megapascals is just megapascals. So it looks like we are left with moving this decimal point 4 places, 1, 2, 3, 4, and we're left with roughly 2,000 megapascals. And that's actually a pretty good number. What it reflects is that water isn't very compressible compared to something like air. That's why the isothermal compressibility of water at 4.5 times 10 to the negative 4th is relatively low. Its inverse, therefore, is quite large. It takes a big change in pressure to affect a relatively small change in density. And what our analysis of the moving wave in the pipe showed was that for a speed of on the order of, say, 1 meter per second, we actually got 14/60th, I believe. So let's just say roughly for speeds in the order of a meter per second, we're going to get about a 1/1000th change in pressure. So this ratio here, change in density. So the ratio of the change in density over the density is going to be 1/1000th. So we multiply 1/1000th times this thing, and we get an approximate change in pressure of 1,000th of this, which is 2.2 megapascals. Now, to put that in context, atmospheric pressure is right around 100 megapascals. So we're going to get a significant jump in pressure as this wave moves through the pipe. And this really is where the hydraulic ram gets its utility. It's from this big jump in pressure when you slam the valve closed, because water is relatively incompressible. It takes a large jump in pressure in order to affect the relatively small change in density that's needed to compress the water. And then if we can find some way to trap our 2.2 megapascals of pressure or thereabouts, we can expect with relatively reasonable flows of water to get pressure changes in the order of 10 to 20 times atmosphere. So what can we do with 2.2 megapascals of pressure? Well, the clearest thing, the simplest thing, what we do with a hydraulic ram is that we use it to lift the water to a higher height. How high can we lift water with 2.2 megapascals of pressure? Well, we can simply consider a column of water at some height h, and we can figure what pressure this column of water exerts at the bottom, and when that pressure is 2.2 megapascals, that essentially tells us how high 2.2 megapascals can lift water, because if the column of water were less than this critical height, you just keep adding pressure at the bottom and it would keep going up. It's once you hit this critical height where the pressure at the bottom is 2.2 megapascals that then the system, by adding pressure or by adding 2.2 megapascals at the bottom, you can no longer lift the water any higher. So what height of water exerts 2.2 megapascals of pressure at its bottom? Well, let's see. We have the height h of the column. We have some area. The height times the area gives us the volume. The volume times the density is going to give us the total mass of the amount of water in this column. And then we can take the total mass and we multiply it by the force of gravity. M times G is going to give us mass times acceleration, force, and then pressure is simply force over area. So the pressure is going to be force over the area of the column. The total mass being the height times the area, that's the volume of the column, times the density of the water in the column. That's the mass. Multiply that by the acceleration due to gravity. Force is mass times acceleration. That gives us the force exerted at the bottom of the column by gravity pushing down all this water above it, and then divide that through by the area of the column, and we get the pressure. So we collect all these terms together, is going to be HA rho, that's the mass times the force due to gravity, G, over the area. Well, we immediately see that the area terms cancel, and we're left with H rho G for the pressure exerted by a column of fluid of constant density and the influence of gravity at a certain height h. Now, it's relatively easy to just toss some numbers in there and get some rough figures. The density of water is roughly 1 gram per cubic centimeter. And let's see, we can convert that to meters, which would give us, let's see, there's power of 2 change there, going from centimeters to meters, but it's cubic, so it's actually a 2 times 3 change. It's a 10 to the 6 grams per cubic meters. And then we want to convert our grams preferably to kilograms, so that brings us down by a factor of 10 to the third, 1,000. So the density of water is roughly 1 gram per cubic centimeter, or 10 to the third kilograms per cubic meter. Force due to gravity is, as we know, 9.8 meters per second squared. For rough purposes, we can approximate that and say 10 meters per second squared. You know, we're off by, 2% there, but these numbers, okay, so the numbers will be right within a couple percent. That's fine. Height, so pressure, and actually we want the height, we know what the pressure is, we want the height in terms of the pressure. So we want height, H, is going to be equal to pressure, P, over rho times G. Well, what's rho times G? It's going to be 10 to the third kilograms per cubic meter times 10, roughly, meters per second squared. So that gives us 10 to the fourth, 10 times 10, kilograms per meter squared, second squared. Kilograms per meter squared, second squared. What a strange looking unit, but if the units come out right, that's usually an indication that, you know, we haven't made at least some silly mistake in the problem. So let's see, plugging in 2.2 megapascals, but what would that be in these terms? A pascal is a Newton per cubic meter. Pressure is force over area. A Newton is a kilogram. Force is, you know, Newton's is a unit of force. Force is mass times acceleration. So it's going to be kilogram meters per second squared times 1 over meters squared. So that's going to give us, those are going to cancel, and we're left with kilograms over meters second squared, which is pretty darn close to kilograms meter squared per second squared. In fact, since a pascal is a kilogram per meter second squared, obviously a pascal per meter is going to be a kilogram over meter squared second squared, and that is in fact the unit we've got here. This strange looking kilogram over meter squared per second squared makes a lot more sense if we rewrite it as pascals per meter. And now, clearly the units are going to come out right. The pascals will cancel, and since the inverse meters were in the bottom, we'll get meters out of this thing. So plugging in 2.2 megapascals, which is 2.2 times 10 to the 6th over 10 to the 4th, that's going to give us a height of 2.2 times 10 squared meters, or roughly 220 meters. So a pressure of 2.2 megapascals corresponds to a column of water 220 meters high. In other words, starting with a flow of water through the hydraulic ram at 1 meter per second, that was our starting assumption, that the flow of the water is moving at 1 meter per second. When we slammed the valve closed, we got a change in the density of roughly 1/1000th. That produced a change in the pressure of 2.2 megapascals or thereabout, perhaps only say 1 megapascal, fine. Height of 220 meters, maybe only a height of 100 meters. But that's roughly the area we're talking about in terms of rough units here. That a flow of water at 1 meter per second through the hydraulic ram can generate pressure that can lift the water then 100 meters high. And that is about as far as we can go with the relatively simple analysis here, simply because the actual considerations are going to have to do with things like the flow distribution. The velocity flow certainly is not constant. The valves opening and closing, we're not dealing with a single velocity of the water. As the pump operates, as the spring opens and closes the valve, the velocity changes. But this gives you a rough idea of how a fairly reasonable flow rate of water can generate enough pressure to lift the water to a fairly surprising height. And that is the basic principle of the operation of a hydraulic ram.